Hello, welcome back. This is Calculus by Dr. Oz. Today we're going to wrap up two different techniques that we learned so far. One is the shell method, the other one is the disc or washer method. So we are given a region which is made of y equals radical x and y equals x squared. In one case, we're going to revolve that region about the x-axis. In the second case, we're going to revolve that region about the y-axis. And we're going to get a solid three-dimensional object, and we're going to try to find a volume integral without evaluating it. Okay, so we're going to have the integral, but no evaluation, because this is already a very long question to work on. And in each case, we're going to use both disk and shell method, and you will see like which one is better than the other one. But this way, you can actually see how we apply both techniques for the same problem. Okay, let me just show you what the region looks like. First off, we're going to revolve the region about the x-axis. So I have two different pictures here for you. In one case, we are using the washer method because here the slice that I picked is vertical to the axis of revolution. And in the second case, I'm going to use the shell method. And as you can see from the picture, I took a slice perp to the axis of revolution so that once I revolve it around, I'm going to get a shell. Okay, so and we're going to write down the integrals representing the volume of the three-dimensional object. And in the second part of this question, which is going to be probably another video, okay, so we're going to have the revolution about y-axis. So this picture is referring to me taking a slice parallel to the axis of revolution. That means I'm going to use the shell method because when I revolve this around, right, I'm going to get a shell. Okay, so we're going to write down the corresponding integral, and finally, I'm going to use the washer method so that once as you see, in fact, I got a slice perp to the given axis. Once I revolve that around, right, the y-axis, you're getting a washer. So we're going to find the volume of that. Yeah, in four of those cases, we are not going to evaluate the integrals. But if you are interested, please go ahead and find the volumes and evaluate those integrals. But here, I want to try to show you how we can apply different techniques for the same region revolved around and write down the volume of that three-dimensional object. All right, this was a very long intro. I want to stop right here and let's get started and see what I'm going to do for part one and part two of this question. Again, this could be like 2 videos. All right, let's handle this problem. So we are asked to use the disk and the shell methods all together. So to write down the definite integrals representing the volume of the solid generated by revolving the region bounded between y equals radical x and y equals x squared. And we're going to revolve them around or about x-axis in part A and y-axis in part B. Okay, I'm going to split this into 2 videos. Hopefully, we're going to handle those separately. Okay, let's work on part A. But before we hit the road, why don't you go ahead and use your graphing calculator to plot y equals radical x and y equals x squared. In fact, you also need the intersection points. So you can actually set them equal and solve this equation here. Okay. So why don't we take the square of both sides. So you have x equals x to the 4th. And that it implies that x to the 4th minus x equals 0. X pulled out. X cubed minus 1 equals 0. And this is for your own reference that you have 2 roots. One is x equals 0. The other one is x equals 1. This cubic has 2 other roots, but they are imaginary, so you don't need them. So the only roots that's relevant for this problem are 0 and 1. And please go ahead and graph these two functions for x min to be 0 and x max to be 1. And you can also choose to go with minus 1 and 1 for x min and x max, okay? Just to see the full region. Okay, here we go. this is exactly what my outlook is. Okay. And since we're going to use both disk and shell methods, I also copied the same thing, the same picture with a horizontal type slice. And in the first one, you can see that you have a vertical type slice. Okay. So one quick observation: if you're going to use the if you are going to use the shell method, if you're going to use the disk or washer method here, that means you're using or you're taking a slice perpendicular to the axis of revolution. Here we go. So this is me using, in fact, a washer method. So that I got a slice like this, and that comes with thickness dx. Okay. In the green region, right? That's exactly what the region looks like. And these are the intersection points. And if you're using the shell method, you're gonna choose slices parallel to the axis of revolution. This is my representative slice, and that comes with thickness dy. Okay. And let's just hypothetically revolve those around, see what kind of like shells we get. What kind of shell we get in this case. You get a shell like this, and in this case, or washer case, we're going to get a washer like this with thickness dx. Okay. All right. So in one case, in this case, in fact, the volume is written in terms of x, and in this case, the volume of the shell is written in terms of y. Okay. So let's first look at the washer method. Okay. So we have this disk, we have the inner radius and outer radius. Okay, here we go. So we have two tasks. One is to come up with, let me just put the inner radius, let's say R1 here, or little r. How about little r of x? And I need also the outer radius, right? Now let me represent that by capital R of x. Okay, so the starting point here is that let's say that this slice here is x units far from the y-axis. Okay, so now the y-coordinate of this point and y-coordinate of this point are needed because the difference between these two is going to be exactly this height here, which we don't need, but what we need is just like the y-coordinate of the upper end here, because that's going to be telling us what capital R is, okay? And we're going to need the y-coordinate of this bottom part of the slice to say something about little r. But let's just write it down. So the bottom part of the slice is on the purple curve, which is x squared, right? So this is y equals x squared, and this blue is y equals radical x, right? So for that reason, little r of x is going to be exactly equal to x squared. Okay, that's the y coordinate of this point here. Okay. All right. So how about the y coordinate of this point? Well, that's on the blue curve, which is the top end of the slice, right? So that is radical x. So I can go ahead and write here that this is radical x. So let me just write them clean here. So capital R of x is radical x. Little r of x is x squared. Okay. So that I can clean this part a little bit so we can see everything probably better. Okay. To be able to write down the volume of the washer, you're going to use the outer and inner radii. Okay, let me just clean right here so I can write the volume of the representative washer. Pi times the outer radii squared minus inner radii squared times dx. And here the x's are ranging in the green region. They're ranging in between 0 and 1. So I'm going to go ahead and choose the interval 0 and 1. Okay. Let's go ahead and write down the volume integral. We don't need to evaluate that. We just need to write it down. So integral from 0 to 1. Okay, integral from 0 to 1. Let me just maybe write it down here. Okay, 0 to 1. Pi times, pi is out, r squared, so radical x squared minus x squared, that's little r squared, times dx. Okay, again, we're not evaluating this, and you can pause the video anytime and evaluate this, this volume integral. Okay, so right now I'm going to go ahead and look at the shell method and write down the volume formula for that. Okay. All right, the starting point. Let's say like this shell coming with thickness dy is y units far from the axis of revolution. Let's say like this is equal to y. Okay. And that's in fact the p of x, right? The radius. Okay, so let me just clean that part maybe. So this distance here, let's clean this as well. So this distance here is p of y, which is y, and I'm going to move dy right here. Okay. All right, so now that this is a little bit more cleaner. So all I need right now is the height of the slice. So to find that, I need this distance here. Okay. I also need this distance here. Okay. Let's see how we can find it. This is, by the way, y equals radical x, and this is y equals x squared. So this is y equals radical x, y equals x squared. Okay. So the very left end of the slice is on the blue curve, and the very right end of the slice is on the purple curve. And both points, both red marks, come with the y coordinate to be exactly equal to y. And the x coordinate of the very left end is going to tell me exactly what this distance is, okay? Which is, in fact, let's look at the blue curve. Blue curve is y equals radical x. I need the x portion of that, so this is also equivalent to x equals y squared. So here we go. This part is just y squared. Okay. And I also need the x representation of this. Okay, so x representation of that is just radical y. And that's in fact the very the x coordinate of the very right end of the slice. Okay, so that determines this distance to be radical y. Okay. So then the height of the slice, so which is h of y. I'm just write right here, h of y is the difference between radical y, difference of what? Radical y and y squared. Okay? And p of y is already equal to y. And let's look at the intersection. We already checked that. That happens at x equals 1. But when x equals 1, y is equal to 1. Okay? So, so let me just clean this part to say that the y's within the region, are ranging in between 0 and 1, as you see. So I'm going to go ahead and write down the interval for y to be 0 and 1. Okay. Let me write down the volume formula. So it's going to be what? 2 pi times the radius. 2 pi. Well, let's also write down the integral from 0 to 1. Radius y times the height, radical y minus y squared times the thickness. Okay, we're not evaluating this integral because we are told not to do so. But that's the end of that. So we were able to write down the same volume in terms of dy. And in the previous part, we wrote the same volume in terms of dx by using the washer method. Okay. Now, in this case, we used the washer method, so we got a vertical slice. And in the other case, we got a horizontal slice, and we used the shell method. Okay. It's up to you to use whichever the technique you want to use. But at the end of the day, remember, you're going to evaluate an integral, and that integral should be integrable. Okay. Like in this particular case, both integrals are good to work with because you could use the power rule for integration. Okay, these are nice integrals, but this may not be the case for other types of questions. All right, so I'm going to finish this video right here, but there's also the part B, and please continue to my next video to see what I'm going to do for part B. Bye.